We are now start our talk. My backstage will put the first question in. Here we go. It's a question to Rohm addressed to the article that you discussed about short circuit detection using the standard DSAT method. Are there other methods that can be used?
Okay,
that's to Felipe Filsecker.
Yeah, thank you for the question, Bodo. Well, in the article, just to give you some context for the other people that haven't read it, I was presenting our new generation of silicon carbide MOSFETs. And what I wanted to show is that, because we get this question from many customers, that if they want to use the short circuit detection, what are the options they have? And what we showed in this article was that you can use a standard DSAT protection, as many of you know from IGBTs. And we set up an example with a standard gate driver from us that has this DSAT short circuit protection, and show that the device was able to turn off in a short time. I think it was in total less than 2 microseconds without any problems. So now other customers say, yes, that's nice, but I would also like to have a different method for extra, say, robustness of the circuit, or maybe because they are using other ways of detecting these short circuit events. And for this, we haven't done tests with the MOSFETs in our lab, but we have gate drivers that integrate a different way of detecting short circuit. And this is not through the DSAT pin, but through the shunt pin. So the devices, if you're using discrete devices, you might have a shunt somewhere, and you can connect this shunt, the voltage measurement of the shunt, to the IC, and the IC will react as an overcurrent detection event that you can set, and you can also trigger a specific turn-off mechanism with a different gate resistance value to handle this short circuit event.
Thank you, Philip. The question is addressed to Microchip, and what are the motivations for increase the voltage levels of SiC power devices?
Hey, Bodo, do you hear me? Is this question for me?
Absolutely, Tomas.
Okay, so I'm not sure if my headphones are ready, but so I will be a little bit more close to my laptop. So yeah, so what is the motivation? So I think the article in your magazine is speaking about 1700 volt silicon carbide MOSFETs, and then as you know, we have in portfolio even 3.3 kilovolt versions of our silicon carbide MOSFET. So the motivation is quite clear. First of all, we see for many years the voltage levels of silicon carbide MOSFET has been dictated by the grid voltages. So we see 600 volts, 1200 volts, and so on and so on. But introducing new silicon carbide technology to the market, I think everything gonna be changed, and this is the one thing that motivation is to offer and to utilize the maximum performance from the silicon carbide, at the voltage levels which we are very close to the standard voltage levels. For example, system levels today are increasing in EVs. For example, we see 800 volts. Solar application, we see 1000 volts. So it's quite very close to the voltage levels, and there is no safety margin. Okay, during the switching, we know the silicon carbide. It's first of all high voltage. And secondly, it's a relatively fast device, inducing a lot of over voltages and some let's say, oscillations. So the motivation is to really increase the voltage safety margin, cover today really different voltage levels, system voltage levels on the market, like solar and EVs and tractions, and then to cover different markets. Okay, so the markets like transportation, railway applications, and
Absolutely,
many other. Yeah.
Traction and railways require quite a high voltage class.
Yeah, exactly. And then and I have another one application was for vessels and ships of fuel cells converters, DC-DC converters, converting relatively low fuel cells voltages, 200, 300 volts nominal, up to 1000 volts. So this is another interesting segments we want to cover. Then, I think another point is the optimization. I think today the system level voltages are increasing to really reduce the DC losses in the systems, but I think I think when we find the right margin and safety margin, we know the silicon carbide is fast and how much margin we need when the silicon carbide is switching. So we can much better optimize the silicon carbide to get maximum efficiency and performance from this. For example, I have a customer asking for 2000 volts. So this is something between. So and the reason is really to get the maximum from the device, and to provide the best performance, best efficiency, which is today required everywhere. So that's all from my side.
The question to CISSOID: is there not risk of EMC or coupling by integrating the gate driver so closely with the power module?
Yeah, so that's a question for me. Yeah, so of course, when you are working with silicon carbide device that are switching very fast and generating high DIDT, you always face EMC issue. And so, for example, in the development of this intelligent power module, integrating the power module and the gate driver together, we faced, for example, coupling issues, but these issues have been solved, and this is the advantage that the customer get with this solution, is that these issues are solved. And when using this IPM, you can focus on higher level system design.
Okay. Thank you, Pierre.
You're welcome.
Yeah, this one is for me. So the benefits that silicon mobility control solution bring to SiC power module. So maybe just to remember that silicon mobility is a semiconductor and software company. So we are selling a specific controller to interface with gate driver and power module to control inverter and electric machine. It's a differentiated technology, bringing a lot of real-time performances, enabling to support advanced control method. So the first advantage is to provide a solution that switch at high frequency and to get the best benefits of the SiC power module. So for example, we can switch at up to 50 kilohertz, so we can regulate a complex electric machine at more than 50 kilohertz using a SiC power module. Afterward, this real-time computing platform bring many additional benefits, like the ability to support advanced control method, reducing losses at the inverter and the electric machine level, supporting also high-speed machine with a high level of number of pairs pole. We can also provide modulation based on angle base compared to traditional periodic modulation. we support also complex dead time compensation mechanism. So this real-time control solution combining hardware and software enable today to get the best performance of the SiC base inverter. Thank you.
Thank you, Patrice. So the next question can come up. It's again to Rohm. Could you please comment in a bit more detail how the internal capacitance have been adapted in the fourth generation SiC power MOSFETs in comparison to the third generation?
Okay, sure. I can comment on that. So one of the problems that we had with the third generation, that we knew it was an issue for many of our customers, was that the device tended to how do you call it, to have this crosstalk effect in a half bridge. So that means when the high side device turned on or off, you had a signal that transferred to the gate of the complementary device, which caused the so-called parasitic turn on. And this is an unwanted partial turn on of the device, which at the end translated in higher losses. So the devices could still work, but it was not optimized. And now for the new generation, what we took care is that we adjust the ratio of the capacitances of the gate drain and gate source capacitances in such a way that this crosstalk effect is not present anymore, or at least not in such a way that the device will have higher losses. Before, we were recommending to our customer, please ensure that the device is actively turned off during off state, so that is using a gate driver with a Miller clamp function. Now we say it's up to you. So if you think that the application would profit from a Miller clamp function, then do it, but it's not required anymore by the device. So that was one important adjustment that we did for the last generation. And the other adjustment was to tune the device for fast switching. So we wanted to have a good performance during fast switching. And for this, we tried to reduce the gate drain capacitance as much as possible, so that the device can swiftly change from off to on state and vice versa. And yeah, now we have the device there, and we have done tests that corroborate this change. And yeah, in some cases, now it's the other way. If the device is switching with a low RG value, it might be too fast for the application. And in that case, you need to limit DVDT by increasing the gate resistance value. So yeah, that would be my answer.
Philip. The question to Microchip again. What are the application benefits of 1700 volt SiC MOSFETs voltage level against 1200 volt voltage class? I think we had previous an answer in that, but
may I continue?
Go ahead, Tomas.
Okay, good. I think again 17 and 1200 volts, of course, there are mainly the benefits. I already mentioned that when we see the many applications that the system voltage level in DC links mainly it's increasing. So the special application, as I said, laser generators, pulse, pulse generators, I don't know, plasma generators or emulators, battery emulators, or railway applications. These applications, even EVs today, are very close to the 1000 voltage, and there is a margin, let's say 200 volts with the standard 1200 volts version class, could be tight at some let's say corners. Okay, so in some operating conditions. So that's what I'm solving almost every day. So just okay. So people are asking, what is the real breakdown voltage of the silicon 1200 volt silicon carbide? Because they are scary that they can be a little bit over the 1200 volts. Of course, data sheet is data sheet. What is there? We cannot guarantee any over voltage through this voltage through this nominal breakdown voltage. So that's the advantage of the 70. So this is natural step how to increase the, as I said already, safety margin, so the customer can really get maximum. Doesn't need to slow down the switch to really keep the voltage in the safe levels. So they really can release the full power of this device. So this is the one reason. Second reason is to really cover some applications which silicon carbide. Sometimes we see that we are forgetting for some customers. They would like use silicon carbide, but there is no voltage levels they need. So this is another benefit that for us, I think is to really promote and spread the silicon carbide to more applications, to more customers.
Thank you, Tomas. And it's obvious, if you have applications where you have inductive load, you always have to face the risk of higher voltages switching inductive loads. If it's a supply or if it's a motor, so you have to have safety margins.
Exactly, and then another one. If I can, I will add some more. So one of the great application for 1700 volts is auxiliary power units in trains. The customers are using the resonant mode converters. So then of course the resonant mode converters are, like generating a little bit more higher voltage peaks. So and this is exactly perfect application for this. Including the good safety margin. So yeah, you are right, and yeah, we are covering a lot of more customers.
Tomas, thank you. Let me see what the backstage brings up. It's a question to Rohm again. You showed in the article that half-bridge EV keys for discrete devices are available. Are you thinking of releasing other EV keys?
Yeah, thanks for the question. So for the ones that are not used to this word,
Philip,
EK.
Yeah, please explain to the general audience what's an EV key.
Yeah, that's the way I used in the article to abbreviate evaluation kit. So it's a board. It's a board for evaluation of the technology.
Yeah.
And in this article, I mentioned and showed also a photograph of the evaluation kit that we prepared for the new generation of silicon carbide MOSFETs. It's a basic evaluation kit in a half-bridge configuration for SMD devices. And there is also another evaluation kit, similar in function, but dedicated to the TO247 version of this silicon carbide MOSFET generation. And we have also gotten questions from customers asking for maybe a more, let's say, an evaluation board that is closer to an application that they might have. And for this, we are preparing something. Actually, it is going to be published soon in Bodos Power. You will see it, I think it's scheduled for the August release of the magazine. And it is a new evaluation kit with the totem pole topology. So we have a single phase TFC board that uses two silicon carbide MOSFETs for fast switching, and the other half-bridge leg has superjunction MOSFETs that switch with the line frequency. And yeah, more details will be available in this article that will be published soon.
Thank you, Philip. A question to Microchip again. What application segments 1700 volt SiC devices are targeting? I think we had already a good explanation.
Right. So yeah, thank you, Bodo, for the question. I think I already mentioned a lot of applications where we are targeting, and maybe I can add more as a heavy industry using 690 VAC voltage grid, industry grid. This is another application. Again, heavy industries, and of course, but in general, not 1700 volt or maybe 3.3 kilowatt we already released. It's really targeting the higher power levels and penetrate the silicon carbide to this area. We see the potential there, and customers, I like it. So I think more power, more higher voltage. So this is on all applications there, including transportation. I said the transportation is huge, including vessels, ships, and so on. So I think, but even let's see what the market with the EVs and batteries. Okay, we see the trend there to increasing the voltage. It's a little bit, still questionable if higher voltage lithium-ion batteries are safety or no, or is a good idea. But definitely higher classes cars are there already, and yeah. So I think in the end, they will need a little bit more voltage levels, power switches. So yeah, partially we can consider this application too.
Maybe I can make an addition here.
Yeah.
It is also the renewable power we should never forget. As you know, renewables like windmills is something where we see the 1700 volt come in or already been installed. So this is a part we have never touched before, because this was something where IGBTs were in use, but silicon carbide is heavily in use in the modules.
Thank you, Pierre. No, Erich. That question, I think, had already addressed and answered.
Yeah, exactly. So
between Gen 3 and Gen 4. You might just, Philip, summarize it shortly again.
So, as I mentioned before, the new devices, this new structure that we labeled as the fourth generation, has had some changes regarding the different parasitic capacitance in the devices, and I would say that one of the main design targets for this new generation compared to the third one was to improve the performance of the device regarding crosstalk and parasitic turn-on. And what you see now is a device that is much more immune to this effect than the previous version.
Thank you, Philip. To Microchip, following questions. Can higher voltage levels of SiC power devices help to simplify usage, replace of the multi-level topologies, or in general simplify power conversions efforts in general?
Wow, yeah. So it's a thank you. It's a quite good question, and quite difficult question. And I think how a little bit higher price of silicon carbide can compensate things is exactly this, to replace. No. Okay, so why we are using the multi-level topologies, right? We need to, first of all, in the case we need a higher quality of output AC line, and use 3, 5, and 7 and more levels. Okay, so I think it's clear. But if there is no clearly needs this, and we need only to block the complete high voltage DC link, that doesn't make a sense to use multi-level. And I believe it's more or less my personal opinion is to use the standard half bridge and simplify the things. If we have higher voltage class silicon carbide MOSFETs, so and this is exactly this point. I don't know if I'm sure our audience, people in audience, knows how difficult it is to, first of all, design, for example, module or in discrete based multi-level converters. It needs a lot of resources. The asymmetrical losses inside is very difficult to design. Layout inside the module. All is difficult. Resources, PWM, computation, you need signals, you need the balancing the DC links, through the capacitor dividers. So this is another capacitors. We know it's very, let's say, the weak point in the converter. It's not really reliable and long lifetime component. And we need to, in the multi-level converters, we need stacked, and created, and then
Thomas.
measure the voltage. Sorry?
Yeah, Thomas, to me, if you have a multi-level converter, you have the amount of devices multiplied by the number of levels. That gives you, for reliability, the multiplied amount of semiconductors to be safe and secure operating. So if you have a one-stage converter, then you will be absolutely in better shape than in a multi-level design. That's my opinion as an old man, having played around with the IGBTs in the past. Okay, could go to the next question. Could you comment if lower CGD in the fourth gen of Rohm's SiC power MOSFETs is achieved by asymmetric trench or double trench SiC MOSFET design?
Okay,
Philip.
so in our case, the fourth generation was, so let's say, kept the same principle as in the third generation. That means we are not using asymmetric trench structure as other company does. We are still using this double trench structure, which was improved in a way to allow the device to achieve a better performance. So basically, we are improving the old technology and not changing to a different kind of trench structure.
Thank you, Philip. What's the impact of higher voltage on Rohm and switching losses? That's a question to Microchip.
Thank you, Bodo. I think could be dramatic, right? So because the thickness of the drift zone, it's somehow dictating the voltage class in one side, another side, increasing the RDS on. So I think it. But if what we believe in Microchip, if you believe the design and fine tune the structure, so the increase from, for example, 1200 volt to 1700 volt, it's not so dramatic. So in principle, there is a little increase of the RDS on and little increase in the switching losses, but not really dramatic. And
okay,
regarding
for the RDS on, you can play with the die size to
Yeah.
reduce it to the. Yeah.
But this is what we don't want to do. Of course, it's thing the step nobody wants to do to increase the die size. But you are right. There are a lot of variables, a lot of parameters we can change to optimize the 17, 3.3 kilovolt, or even higher voltages to get good ratio between the RDS on and switching speeds and losses, and a good safety margin in the breakdown voltage. So between 1217 there is no big difference. Of course there is. Maybe important is a difference in the temperature coefficient of the RDS on. It's changing quite in the good way in the negative temperatures, but of course in the positive temperatures where we see the positive temperature coefficient is a little bit increased. So this is another point of view. So, but the increase in the breakdown voltage, from system level point of view, bring a lot of advantages and the safety things and the quality, and of course increase the voltage in the DC link, reduce the current in the system, and like this improve the efficiency and the performance. That's clear. So yeah, there is difference, of course.
Okay, Tomas. The next question to Rohm. For the 1200 volt, what's the minimum R on for the large SiC die for this new generation? So we first need to know what's the die size. Larger SiC die is, to me, not a specification, but Philip, you can specify, because the larger die size does not say too much.
Yeah. Well, what we are considering now, we have, let's say, two categories. One is are the devices that we offer in a packaged form. That is, in this case, a TO247 device, for example. And for these devices, the largest die that we offer corresponds to an 18 milliohm die for 1200 volt devices. But we also have, in the case of per die product, a die that is rated for, let me check here, yeah, 11 milliohm. So that would be the largest die.
And that's in the TO247.
No. The 11 milliohm one is a bare die product. So
it's bare die.
Not considering packaging it.
Okay, that will be then find its way into module applications.
Exactly. So it was mainly designed with the application of powertrain inverters in mind.
Okay. Thank you, Philip. It's a question to CISSOID. What's the benefit of integrating the controller board with the SiC IPM?
Yeah. So I can answer to that one, and maybe Patrice can also comment. So offering intelligent power module, we were already integrating the gate driver together with the power module. The idea was already to accelerate the design cycle for our customers. And so adding the controller board, we are going one step further. So we add the higher level of control. So not only with the hardware, but also with all the flexibility offered by the software. And so in this partnership with Silicon Mobility, CISSOID is offering the hardware platform, and Silicon Mobility is offering the microprocessor and the software with a lot of flexibility and control algorithms, but maybe Patrice can comment on what they are offering in terms of software.
Yes, the global solution is an answer to the market demand to go very fast, I think, and to be flexible in order to support customization, and together combining CISSOID power module and expertise and software from Silicon Mobility. We address these needs. So we are providing the software to control and also all the ecosystem for configuring and calibrating the system on a motor bench and also on a running vehicle.
To me, the temperature range for microcontroller is in a different lower range than for power devices. So the power devices, if we look to SiC, can go up to 200 degrees Celsius easily, and the microcontroller should be in the 85 degrees range, what I have in memory.
So we are a little bit higher than that, and we are supporting, and we have been qualified IEC 100 grade 1, so up to 125 ambient temperature. And together with this system, CISSOID is also providing a reference cooler in order to cool the system, which is very much integrated, but that I think has a good cooling system solution.
Yeah, so if I can add, so our power module are liquid cooled, and so with liquid cooling, you extract the heat from the bottom. So in principle, you are not heating too much the control device, which is not totally the case. But of course, the gate driver and even the control board is dissipating still a bit. And this is also heating the air inside the power cabinet. And so if you want to really to reach high power density, you need also to have the control board and the gate driver sustaining higher temperature. And the solution we provide can sustain an ambient temperature of 125 degrees C, which is indeed above of the typical 85 degrees C that you find generally on the shelf.
Okay, Pierre.
So we are providing headroom in terms of thermal sizing and power density.
Okay, sounds good. Again to Rohm. That's a very complicated question. Can the customer order 11 milliohm with a reasonable lead time?
Yes, it's a tricky question. So, as I mentioned before, the 11 milliohm dies have been developed with the application of powertrain inverters in mind. With this, you can already think that actually the interested customers are probably considering the very large volumes. And actually, we are not considering projects where the volumes are low. This is now not a priority because of the high volume demand from the large automotive customers. So it will be very difficult to obtain this kind of product for a small project. I would encourage still to contact us and try, because we, for this kind of products, we analyze it case by case, and there are also some strategically attractive projects that we are also supporting, even though the volume might not be as high as in other cases.
Okay. Felipe. Thank you. Okay. That's a question to the RDS on increase at maximum rated junction temperature. Normally we find this in the data sheet.
Shall I ask, Felipe? Sorry, may I ask? So this is for Rohm and Microchip. So may I start?
Yeah, Felipe.
Okay.
Yeah, please
If
start.
you like.
I
Yeah.
Yeah. Okay. So if I understand the question right, so I think of what is the typical increase in the RDS on the temperatures, right? Or the maximum temperature. Yeah, I think yeah. So I think I am very proud to announce that Microchip has very good let's say temperature coefficient of this parameter. Typically it depends on the voltage levels, as I've been speaking about it, so it really depends. Let's say 6, 7, 8, 900 volts versions are really have a negative temperature coefficient at the negative temperatures, and then it's increasing slightly, could be let's say maximum twice the nominal RDS zone, or 1.8 or higher. It's getting better, but the temperature coefficient is getting to be more important at the positive temperatures. So at the maximum temperature could be for us, for Microchip, is it's very good. I think if you are calculating in your system with this, you can really get good. You know, I think it's important to calculate with this temperature coefficient in your operating case, and for Microchip is somewhere around 1.7, 1.8 times nominal RDS on.
Okay, thank you, Tomas. Any comments added?
Okay, if no comments, I would like to add that in our case, the trench device has let's say a stronger temperature coefficient than the planar version that we had. That would be our second generation. So in this case, the temperature coefficient when going from room temperature, that is 25 degrees Celsius, to the maximum allowable junction temperature, which would be 175 degrees, it's roughly of 3 times.
Okay. Thank you, Philip. What happens with the breakdown voltage in SiC MOSFETs over temperature? At high temperature, does the breakdown voltage drop with respect to room temperature? Datasheet rating. So that's just a question. If the breakdown voltage has been affected by the temperature.
Yes, I can answer maybe the first one, and then Felipe the second one part. I think the higher temperature means higher breakdown voltage. It's quite common. I'm not sure. It depends maybe on the technology and on the voltage classes again, but in general, you know, there is a positive temperature coefficient, means higher temperature, higher breakdown voltage. And maybe the second question was. I'm not sure if there is a. Can you remind me, Bodo, please?
Let's get the question again on the screen. I think it's a question in general about what happens over temperature, and specific at high temperature. If it drops in respect to room temperature, datasheet rating. I think you answered it.
Yeah, but I think the breakdown voltage is not problem at this high or maximum junction temperatures. Problem gonna be everything around. You know, it's breakdown voltage it's a problem if voltages, you know, it's over voltage, but at the high temperatures, I think you're gonna have a problem with the other bonding and lifetime, and you know, it's the dies of course withstand this voltage, but it's really not. We don't recommend to operate the die in these levels. I think if we have in the data sheet 175 C degree. Of course, your operating temperature of the junction will be much lower to have the margin, because the margin is important to cover some overloads and other events.
I understand that the lifetime of the device should be taken in consideration, not to work at the border of the temperature capability. Okay, so could you comment on the thickness of new generation SiC power MOSFET dies? Is it improved to older gens? That's a tricky question. What means improved? What I learned is if we get to thinner material, it's better for the thermal impedance. So the question to me must be how thin you can get your die. Is this an improvement over time to make it more efficient in the thermal behavior? Who will start telling us?
I think I can start. So
Okay.
in our case, well, I already mentioned that we worked on the structure, on the trench structure to improve the device, basically the dynamic characteristics of the device. But I didn't mention that another part of the improvement, which is mostly related to the static characteristic, that is the conduction losses of the device, was also achieved through a thinner die. So we are talking about vertical devices. So if we can shrink the device on the vertical axis, we will have also an improvement of the conduction losses. And this was also part of the improvements that Rohm included in the new generation.
Okay. Thank you, Felipe. Looking at the 1700 volt SiC organ versus lower voltage silicium solutions is not really apples to apples, but it does nail down how high voltage, low capacitance and no RR allow going back to simple stupid head switching. Did the SI solution, the silicon solution design, get a SiC switch and diode only upgrade to show its efficiency? I think that's a question in general. A drop-in solution is not normally, in most cases, the new design will bring the total benefit.
Yeah, so if I can start.
Go ahead, Tomas.
So then I think we should somehow separate, you know, the silicon carbide or any semiconductor power switch and how we will switch them, if it's hard switching or soft switching or in the multi-level converters, two-level standard half bridge config. This is two things together. Just I think the system level engineers can cover this part, you know, how to switch in the resonant mode. But what we are bringing to you is really switch which are very close to the ideal switch we learn at the university. You know, this is the off, endless RDS, you know, resistance, and on is almost zero RDS on. So this what we are trying to do and give you and provide to you as a customers this let's say almost ideal switch at all voltage levels you can imagine. From 600 voltage, okay, the GaNs are covering much less voltages. Silicon carbide can cover much higher voltages because it's in first case it's bringing you a new level of speed. Okay, so I can give you example. I have a customer. We have tested our 3.3 kilovolt dies or the discrete packages, and say they never seen something in this class level, something fast. Do you hear me?
Yeah.
Monsieur Rabak.
Yeah. So I think it gives you new level of you know, options. And then maybe another example is another customer, a DC-DC converter. I think around 300 kilowatt in APU unit, silicon carbide on the primary and secondary side. They have a problem to develop the passive. The transformer can handle this switching frequency, but they have the strain of you know, the line was the strain, and you know, the in the strain that, you know, this is the problem, that we are now a little bit, you know, far away from the passives and the other things, but this is the problem. I would say this is no problem, but this is an issue for the system level engineers, how to solve it. We just give you the tool, use it.
Okay, thank you, Tomas. The question to CISSOID: do you have your own SiC MOSFET bare dies, and are you open for selling?
The answer is simple. It is no. So we are developing our own gate driver ICs, but for the SiC bare dies, we are buying from multiple suppliers, but it's not our own die.
Thank you, Pierre.
You're welcome.
We had a great, fruitful discussion, and I will thank you all joining the stage and joining in the auditorium. And I'm going to the beach until the next session will come. That's the fish. Yeah, it's only a few steps over, but that's the joke. We are living at the Baltic Sea at a nice place. Thank you, ladies and gentlemen.